Hello everyone! And yeah, this is quite a different intro than normal, but happy Physics Friday. What I actually wanted to do in this video, aside from having an excuse to play Minecraft, is determine this acceleration of gravity inside the game. And this might seem, quite silly and almost trivial, in the sense that, well, I mean, it's not too hard to, drop one thing and, then calculate how long it takes, to fall and plug that into a formula to find G. Like, no, that's not hard. But what does make things a little bit difficult is the following. This right here is 30 blocks tall, right? And if I go ahead and press this button and spawn a pig from that height, you'll see it goes whee and then splat, right? R.I.P. pig, I'm sorry. But the amount of time this takes, I recorded it earlier and recorded it, is about 1.15 seconds. So you might say, okay, well, fair enough. I mean, that seems maybe reasonable. So then you go over here, and press this button. This is now 50 blocks. And the pig falls and unfortunately does not make it. But that takes 2.01 seconds about. There could be some lag or some frame issues, but those are the two numbers we got. And then we do it again for 100 blocks, right? Whee! And then splat. And that right there took about 3.02 seconds from what I got earlier. And the interesting part about this actually is whenever you go and use this little formula over here, the gravity is equal to, or the force of gravity is equal to 2 times the height divided by time squared. The values for G we get are actually quite different. So for the first one, we end up getting about 26.31. New line. Oh my goodness, I'm at least editing signs. 26. Let me see Desmos. 26.31. Meters per second squared. Right. I'm like that's the only time I'm writing units. They're applied from now on. And for this one, it's about 24.75. Which really isn't a huge difference. And you might be saying, well, that's not necessarily a cause for pause or suspicion that anything else is going on. However, once we go over to here, right, this 3.021, the amount of time, or sorry, not time, the G we calculate, assuming that the acceleration of gravity is constant, is 21.93 seconds. And what you would actually expect for such a high drop like this is for, assuming a constant acceleration of gravity, is for the effects of lag and anything like that to actually be accounted for more, simply because, well, it's a higher drop. But we find actually, I should pick that up, that is the exact opposite. And it's because of this that I believe there's probably a speed limit. So if you drop something in Minecraft, it's basically capping your speed at a certain point. However, what I want to find out is sort of the nature of that, whether or not there is some force of drag, whether it be like Stokes drag or like more Newtonian drag, or if it simply is literally just a cap of your speed. So that's kind of what I want to figure out today. And by doing that, well, here's our motivation. And by doing that, or to do that, I should say, I am going to be yeeting myself off of a couple of towers. So yeah, let's get to it. So the way this is going to work is really the following. I am going to press this button right here, and it's going to drop me. And then after I fall, what I'm going to do is go to my little editing software, and you'll see this number in the top left-hand corner, the third one, the 86.00000. My y-coordinate right there. What I'm going to do is literally just get a bunch of data from that and just plot it onto Desmos, or log it first, plot it onto Desmos, and we're going to see essentially if there is indeed a trend. And from that, we could maybe run a regression or something of that sort to try to calculate G. So, here goes nothing. I'm just going to hit this. Whee! Okay, that's trial number 1. Let's go on to trial number 2. So this is the 50 blocks up here. Just gonna drop. Whee! Okay, next, the 100 block one. I should have frozen the daytime, but that's alright. It's gonna go now. Quite high up, but that's alright. And there we go. So, what I'm going to do now is go into the editing software and see how long each of those took.
A few moments later.
So, each run that I did took about the same time it did originally with the pig. But you might notice here that I did an extra fourth one from actually quite high up. And I just wanted to see how this one would compare because I realized that, it'd be a 30, 50, and 100 blocks. I thought 250 could, or well, really 251, would be a good point of comparison as well. And it does, I think, illuminate a couple of things. But in doing this, here's all the data right here. I'll add these links in the description. But basically, here is all of the data. Basically, just like time intervals. I chose this rather arbitrarily, just 0.25 second intervals because those are easy to type in. And I just plot them. But what I did was 3 types of estimations. I just assumed, for one estimation, it's just parabolic. Assume that the force of gravity is constant on each, not dependent on any other variables, and from that, estimate g. So, thank goodness Desmos has regression. Oh my gosh, thank you. But from this, we can see quite a few things. So for this first one right here, I can actually turn these on. You can kind of see, but you can see from these right here that from the first one, we estimate g is about 25.88, right? And on the second one's also 25.2, so slightly lower. I'm ignoring the negative signs. For g, it's just a directional thing. If I threw a negative in front of here, it would literally just switch the sign of the g or the a. But basically, what you'll see, the trend here is basically it gets smaller and smaller as you go. For the parabolic estimation, the higher up you go, the lower g turns out to be. I say b in kind of air quotes right here, because it seems like there's a trend. It's like about 25, it's about 25, and then all of a sudden it drops to 22 and like 17, or closer to 18 really. And it was because of that that we originally said, all right, well, maybe this isn't the entire story. Maybe there is some sort of drag that the game is taking into account. And that does seem to be the case. Maybe. This is one of the strangest things I've seen in a very long time. But you'll actually notice that for the rest of these regressions, for both the Newtonian and Stokes, the R squared values are, I haven't checked every single one, but like basically higher than every single parabolic estimation, which is quite interesting. And it should be noted that both only do have 2 degrees of freedom, so you can only vary A and C here. And here you can only vary like C4 and G4, should be noted. And same thing for the, let's show that for the Stokes drag real quick. But basically here, what we have, look at the R squared, it's all 0.999. I think this is 1 for some of them as well. But basically, what we have here is rather interesting because it's what it's saying, what it's saying G is not consistent at all. Like for the first one, for example, even though it fits the data, extremely well, better than the parabola ever could. And the R squared value is 0.9999. It says G4 is 27, which is quite different. Actually, it's not that too different from 25. I am mistaken. But once we start, oh, pardon me. That's Y4. Oh gosh. Yeah, no. 17 is very different from 27. There's a huge difference. Pardon me. I should have put these in order. Anyways, moving on from that. If you look at the the third one right here. So this right here, it says G is 29, and then it says G is 30, and then it says G is 43. And obviously, it doesn't make sense for in Minecraft, the gravity to be like, changing depending on, how high you are. I mean, unless the developers coded it like that, but that would just be weird. But one thing to note is that what is also changing between each of these trials, right, is well, I'm going to call it the drag coefficient. It isn't really. It's a drag coefficient divided by the mass. But these coefficients, C1, C2, and C1, C2, C3, and C4, that basically is estimating, or not estimating, that is essentially the force of drag applied on our character. So in giving it these 2 degrees of freedom, it figures out a way to, yes, minimize the r squared value, but it's not giving us a consistent answer for g, and also the drag coefficient is all over the place. It makes no sense for our character to have, it makes no sense for the player to have a different amount of, drag depending on how high they are. I mean, that doesn't really make sense, does it? It doesn't make sense for the developers to code it like that. So this is all very suspicious with this data right here. But if we go on to the next one, for Stokes drag, you'll notice again that all of these fit extremely well. You'll notice here that it's a sort of similar story. You have, for for the first one right here, the force of gravity being estimated quite high. I mean, if you look at the Newtonian one, it's like, what, 43? It's like 50. It's quite high. But then once you start to get down, it says, okay, well, maybe it's like 34 and 33 and 33. So it seems like for the Stokes drag, there's at least a little bit more of a consistent... yeah, see, this is the r squared value. That's 1. It seems like there's a trend that's at least a bit more consistent, where maybe we can say, okay, if we jump off something extremely, extremely high, we can say that g is maybe about 33, right? And it seems like that's the case. I might try this again for like 300 blocks, or maybe even go into like the void or something, or actually above the height limit, I suppose. And go from like 400 and see if Stokes drag does apply. 'Cause this seems to be the most promising for high heights, whereas for whereas I don't know what is going on for the for this first estimation right here, where g is all over the place. Now, you could try to solve this by essentially saying, well, I don't want Desmos to estimate, the drag applied on Steve, or not Steve, sorry, the player really, because I don't have a Steve skin. You could say that. So you could basically, find, or try to at least, estimate the drag coefficient of of Steve, which, oh gosh, there are many ways you could do this. And basically what you would do is, by fixing these values, by fixing the k's in every single one of these, you can try to get g to be some sort of constant thing. So that's what I tried to do, ta-da, in this second Desmos graph, which I will also include in the description. I mean, the parabolic estimations aren't going to change, those are the simplest, but for the Newtonian and Stokes ones, you'll notice that each c is its own, or it's the same between each trial. And if you go into the notes here, you'll see that c right here, c is for the Newtonian one, so that's just 0.7, so that's about the drag coefficient for a person, like skydiving, not like if they're, there's probably a bio word reference to that, but with their stomach, like, this isn't with their stomach facing towards the ground, this is like head first, like they're full on, they're full sending it. And then that's just the average, that's the estimated weight of Steve, 342 kilograms. We're just looking at this now, maybe we should have done the drag coefficient for, not a normal person, because, Minecraft person is rather blocky, but it's alright. This is just an estimation, trying to get a feel for it. And then this one right here, this comes straight out of Stokes' law, so the 6 pi is literally straight out of there. This 0.7816 is basically if you got the volume of Steve, smushed him in a ball, like a big sphere, and then found the radius. That's what that is right there. I just put it in that form because it looks really ugly otherwise. And then this right here is just the dynamic viscosity of air right here is 18.5 times 10 to the negative 6. That's just 18.5 micropascal second, I think. I'm pretty sure those are the units. And again, that's just the Steve's mass right there. So with all that being said, what we can see is that G is at least a tiny bit, maybe more consistent. So if we look at the Newtonian one, at least it says 21, 24, 26, 28. That's it. It's at least all in the 20s, right? And the R-squared values are all, pretty decent anyways. Like, here, I can graph them. Like, they're not perfect. They're not as good as the last ones, but, like, they're still, pretty decent and quite plausible. But if we go over to the Stokes drag, you'll notice that there's quite a big gap here, which is quite ugly. But what you'll notice is that our G values get rather consistent after a while. So you say, just like 27, then 26, then 23, 23. And the interesting thing is that all of these numbers are in the 20s. So it's kind of time for the conclusion. What is the conclusion? What is the force of gravity in Minecraft? Well, if you do a bunch of parabolic estimations, you really don't get a clear answer. There's so much inconsistency. There's some other mechanic going on. Because we don't know what that is, or I don't at least. I'm sure the devs do. If you apply Newtonian drag, you get rather inconsistent answers, and the same thing with Stokes drag. But if you assume Steve to be a person that weighs 342 kilograms, basically what you can find is that the force of gravity in Minecraft is basically anywhere from like 20 to 30 meters per second squared. About? Maybe. Again, that is with some pretty generous assumptions right there. For example, Stokes' law is really only supposed to apply for small spheres, and I don't think Steve is small, but then again, we are assuming other ideal conditions, so it's like, well, anyways. This is just kind of a guess, in all honesty. But if we let the computer decide everything, just kind of run a regression based off the data, we get widely different answers. G ranging from 33 maybe, all the way up to 50, and then down to like 17 or 18. So, in conclusion, we don't know. But we learned quite a bit in the process, and it was all quite fun. So I hope you all enjoyed this rather different video, and see y'all on the next Physics Friday. Thank you for watching.